University of Warsaw. I hope I got your name right.
Yes, absolutely correct.
Thank you. And he will be telling us about the very cleverly named quantum version of the Sudoku, the generally quantum SudoQ and its cardinality. So yeah, I'm looking forward to hearing about this. So the floor is yours, Marcin, please.
Many thanks. Thank you for this introduction. My name is Marcin, and hi everyone. For my presentation, the presentation title is about our work with my colleagues, with Jerzy, Grzegorz, Adam, and Karol, and Professor Karol. So, and the title of this talk is about generally quantum SudoQ and its cardinality. So let's start about my presentation talk plan. So we have 5 parts. So the first part is about introduction. For motivation, the second part is about simple recall about quantum Latin squares definition and Latin squares as a classical case. So the next part is about our conception of cardinality and for SudoQ solution and definition about SudoQ. And the next part provides us a simple case of SudoQ for low-dimensional Hilbert space. And the last part is about conclusions remark. So let's start about simple case, in simple problem. So we consider the constellation of quantum states for a given dimension. Okay, for instance, our dimension is equal to n with the certain specific properties. So it's necessary to say that the first work based on this investigation was a seminal thesis of Zauner. So there is quantum designs. But in general case, we consider discrete structures in a fine dimensional Hilbert space. So the naturally examples of these discrete structures are mutually unbiased spaces. So the another example for these discrete structures are symmetric informationally complete generalized quantum measurements, SIG-POVMs. So let's move to the definition. Maybe not everything is similar to MOOPs and SIG-POVMs. So let's recall that the definition of MOOPs is like we consider 2 orthonormal bases consisting n vectors, each in fine dimensional Hilbert space. And we have equation that that our norm of dot product into the power 2 is equal to 1 over n. So this is the definition. We have 2 vectors and dot products and norm and is equal to 1 over n. Of course, there is a generalization. It means that we consider every pairs for this definition. So the simple example of MOOPs is consider the eigenbasis of our maybe very known operators, Pauli operators. So when we think about this eigenbasis as points on belongs to block sphere, we can imagine that it can form a regular octahedron with the, I think, important properties that the center of summation of this point is centroid. Yes, it means that is in center of in block sphere. So let's recall about symmetric informationally complete POVMs. So we say that that the set of a vector satisfies this equation. The vectors is from the are from Hilbert space, fine dimensional Hilbert space, and satisfy the following equation. So the satisfaction is that we use dot product between two vectors and also norm into the power 2, and this definition is equal. This left hand is equal to 1 over n plus 1. Okay, so based on the previous intuition, we can think about sigmatric information complete POVMs like this, like in low dimensional, like a regular tetrahedron. Of course, our points belongs to block sphere. So there is the same, I think, idea. Yeah, and also we have centroid in our block sphere. So let's recall the classical definition of Latin square. So there is n times n array of n distinct elements arranged so that there is no exist element repairs in any row or column. So the example of the Latin squares in low dimension is like here. So we can observe that we have three colors, yeah, and also symbols, in this case numbers. So, but yeah, and there is Latin squares because there is no elements repairs in any row or column. So let's move to quantum world. So about quantum, so we consider the n times n array of vectors from finite dimensional Hilbert space, arranged in such a way that each row and columns form an orthonormal basis. So there is example of quantum Latin square. We use cat-bra notation to represent our computational basis. Of course, we have naturally mapping, so there is a morphism from mathematical world. So this is a assignment between classical solution and quantum solution. So because we use symbols for representing computational basis, so there is a natural mapping. But in general case, we can consider the different grids. Yes, it means that our quantum world is more complicated than natural. Yeah, it means that we use superposition of our states. We use um, how to say, okay, more complicated tools, yes, but in this case for low dimension Hilbert space is natural thinking like use the this construction. It means that our vectors should form orthonormal basis. So this constraint provides us yeah more and more examples. So let's consider more generalization. So this generalization is thinking about the quantum Latin squares like grid with additional constraints. So these constraints for each these joint blocks of size n should forms an orthonormal basis. And we say that this construction is SudoQ. Okay, so the first how to say, the first concept was in this work. So there is first time to see this concept. Okay, but what else? We provide next level for these concepts. We can think like, okay, so for me, for us, it's interesting thinking about the number of unique vectors from our SudoQ solution. Of course, how to say, quantum war is it's important to think about vectors up to a global phase, of course. So in this case, we also consider the same simplification. Okay, and we say that the number of this vector is cardinality of SudoQ solution. Okay, so for instance, this example has a cardinality of 6. Yes, because if we, how to say, if we count these numbers or colors for better understanding this problem, and we observe the 6 colors. Okay, so let's move to recall, okay, to provide some characterization of our solution. Okay, we say that SudoQ solution is classical when we can build of states from the computational basis, and our cardinality for this solution is equal to n. Generally means that our SudoQ solution has a cardinality greater than n. Upperly SudoQ, so there is a case of SudoQ that our solution contains superposition states not belong to computational basis, but our cardinality is equal to n. Yes, because we can use transformation from unitary rotation to transform to classical Sudoku. Okay, so there is some simplification of our notation. Okay, so what about motivation of this construction? So we can think about that the SudoQ solution can determinize 3 times n into the power 2 orthogonal measurements. Yes, because from vectors we can use, we have dot product, yes, and we can build operator, orthogonal measurement in this case. Of course, it's okay, maybe important to say that this is like from our constraints, like when we consider rows, columns, and block of the solution pattern. So okay, this is example, more complicated than previous. So we consider the row. Of course, in this example, we don't write constant, yes, because it's not necessary. Yes, we drop out constant normalization. Okay, but we have row, of course, and we can use this row to build orthonormal measurements, and also we can use columns, and we can use blocks for this problem. So let's move to I think maybe more easier case than previous, yes, because in previous case we consider a 9 times 9 SudoQ solution, but in 4 times 4 SudoQ we provides a simple characterization of cardinalities. Okay, and from our work, we provide that only admissible cardinalities of 4 times 4 Sudoku are 4, 6, 8, and 16. Okay, so let's move to example. So this is the example showing. This example show us cardinality of 16 up to the constant of normalization. Okay, so let's do a simplification of this solution, because okay, so according to the definition of Sudoku, we can also investigate that we have a set of clues. It means that simple restriction or something like okay, some numbers when some number of vectors belongs to our grid, to our Sudoku Q grid. Okay, so for this example, we have five vectors, 5 clues for our solution. So, and the question is, is it a uniquely solvable Sudoku for 4 times 4? So, and the answer is no. Why? Because there is exist some element, yes, using the following steps to go to solution. Yes, we observe that exist cat2 when we have a problem in this row, of course. Okay, so according to previous intuition that our Sudoku, classical Sudoku puzzle can be transformed into quantum world, like morphism on symbols. Yes, we consider the numbers. We can use these morphisms as consider a cat notation, computational basis. Okay, but in our investigation, it's important. It was important. Fight with this conjecture. Yes, it means that the conjectures from original work. So there is a quantum variant of the popular game. So this conjecture which states that uniquely solvable means having one solution, Sudoku, admits only one solution also in a quantum regime. We formulate a proposition for this case. So this case 4 times 4, yes, we say that uniquely solvable classical Sudoku is also uniquely solvable Sudoku. Okay, so maybe it seems like, how to say, a bit complicated, yes, because our proof based on finding a parameterization for this case. So the parameterization in general case, I think is not, it's not easy. Yes, we use this low dimension to provide a parameterization, and it's okay. It's not too complicated like in general case. But what about we can think like, okay, maybe we can try to build a maximal cardinality Sudoku solution only, yes? So, so it's possible. So, and I will present our results from this work. So, but it's important to change our notation, yes, because we think about vectors belongs to blocks, yes. So, but our now the notation is that when we consider block, uh, will be replaced by matrix. Of course, in this case, our matrix can be treated as vectors from the block. Of course, this example show us okay, this idea. It means that we consider the block and natural mapping into matrix. Of course, this matrix is written in the computational basis. So it's maybe only detail, but it's important in this case. So let's move to statement. Yes. So it's important to say the statement about this construction. Yes. So when we have permutation matrix and families of unitary matrices, indexes by 0 and n minus 1, our grid defined as follow is a proper Sudoku solution. So the proof of this lemma it's not too complicated. It means that we use okay, some properties of tensor matrix tensor product, and yes, and some, of course, assumption about our unitary matrices. But in general, it's not difficult. Yeah, I think. So the next step is formulate more stronger statement about this construction. Yes, we should assume that that if we have tensor products of our unitary matrices has different columns, then our Sudoku Q grid is a solution with the maximal cardinality. It means n into the power 4 for any dimension n. So if you are if you try to some fight with proof, I think that our work can be beneficial for this, but it's not too hard. Yes, but I think that work thinking about this construction, it's maybe complicated in the sense that it's not obvious how to construct the grid like from previous lemma. Okay, so let's consider the last example.
Sorry to interject. You have about 2 minutes.
Okay, thanks. So let's consider the following example. So there is a construction of Sudoku 9 times 9 with maximal cardinality. Okay, so according to concluding remarks, this is a link for our work, and yes, please feel free to ask a question if you want. Many thanks for attention and thanks.